In this video, we'll look at the representation of graph, the data structures used for representing graph. See, for representing a graph, we have to represent two things. What are the set of vertices and also set of edges. So for representing them, there are more than one methods, that is adjacency matrix, adjacency list and compact list. Let us look all of them one by one. Yeah, here first one is adjacency matrix. I have already taken a matrix. The graph is represented as set of vertices and edges, and the number of vertices which is represented as n are 5, and the number of edges that are represented with the symbol E are 7. So I have to represent all those vertices and edges. For representing in the form of a matrix, I have taken a matrix of size 5 cross 5, 5 by 5. The vertices are starting from 1 onwards, so here also I have taken matrices starting from 1 onwards. But really when you use a program, C++ program, it may be starting from 0, so you can start from 0 and you can label the vertices from 0 onwards. Now let us see how to represent that graph in the form of a matrix. See, for any two vertices I and j, if there is an edge, then we should mark 1 inside the matrix at that same location I and j. Let me show you. It means if there is an edge I to j, then mark in a matrix ij as 1. Otherwise, it should be taken as 0, means there is no edge. So let me show you how to mark this one. Let us start from vertex 1. Vertex 1 is having edges connected to 2, 3 and 4. So from 1, there is an edge to 2, there is an edge to 3 and 4. Remaining are zeros. 0 means there is no edge. Then let us look at second. From 2 there are edges to 1 and 3. So from 2 there are edges to 1 and 3, and these are all 0. Likewise, I will fill up for all. From 3 it is to 1, 2, 4 and 5. 1, 2, 4, 5. Then from 4 it is connecting 1 and 3 and 5. 1, 3 and 5. Then from 5 it is connecting to 3 and 4. So from 5 it is on 3 and 4. So that's it. See, if there is no edge, I have marked it as 0. So even you can mark it as infinity in the absence of edge. And one more thing, diagonals are representing self loop like 1 to 1, 2 to 2. There are no self loop here. So sometimes we put infinity there in self loops. So it depends on your application, depends on your requirement. Either you can put the value as a 0 or you can put the value as infinity or any other marker that you want to show absence of an edge. The next, let us look at adjacency list. For representing a graph in the form of an adjacency list, we'll take an array of linked lists. So I'll take an array of size 5. This is an array of size 5. This is an adjacency list. So actually this is array of linked list. Now for each location is representing a vertex. So for that location we will have the set of adjacent vertices. For example, if we take 1, if I take vertex 1, from 1 there are vertices connected to it are 2, 3 and 4. So here we will draw a linked list with those nodes representing 2 and 3 and 4. This is null. Now similarly, who are connected to 2, 1 and 3? So I should have the list of nodes showing 1 and 3. And now similarly for 3, the connected vertices are 1, 2, 4 and 5. I will draw them. Now for 4, connected vertices are 1, 3 and 5. So I will draw 1, 3 and 5 here. 1, 3 and 5. Now for 5, 3 and 4, 3 and 4. So this is array of linked lists showing the edges, and this array itself is showing vertices. So this is the representation. Now I have to show you compact list, but before that let us do some analysis of this one. See, in this matrix there are total 5 into 5 elements are there. Some are zeros and some are ones. So unless we check, we can't know whether there is an edge or not. So for accessing edges, we may have to access all the elements. So total number of elements are depending on the number of vertices, that is n square. So it means any algorithm which is accessing a graph in the form of a adjacency matrix has to access those many elements, process those many elements. So the time taken by an algorithm may be dependent on n square. Then if an algorithm is using adjacency list, then what is the memory consumed here? It is the set of vertices, that is set of vertices v, that is n, plus these are set of edges, but each edge is represented 2 times, so 2 into e I can say, so this is 2e. So the time dependent on set of vertices and set of edges. There it is dependent on square of vertices. So the time taken by any algorithm depends on number of vertices and edges, and it depends which data structure is used by an algorithm. It may be n square or it may be v plus e. 2 times of e is also, we can consider it as e, so it is v plus e. So if you check most of the algorithms, they are analyzed based on v plus e, number of vertices and edges. So that's the analysis of the space consumed by this data structure. Now next, one more thing I will show you, that is weighted graph. See here I have given weights to the edges of a graph. If weights are given, then we want to store those weights also. Means the cost of this edge is 9, the cost of this edge is 6, and the cost of this edge is 8. So we want to store those weights also. So how to store that? So in the form of a adjacency matrix, instead of marking this as 1, this edge as 1, we can mark it with a weight, that is 9. So edge from 1 to 2 is 9, and the cost of edge from 1 to 3 is 4. Cost of an edge from 1 to 4 is 6. So in this way, all these ones can be changed in the form of a weights of those edges. I'll change them. So here I have changed all of them. Now we can call this as cost adjacency matrix. Instead of just calling it as adjacency matrix, we call it as cost adjacency matrix, because the matrix is representing the cost of edges. Then how to represent those weights in a adjacency list? See here, for the vertex 1 I must have all these vertices which are adjacent. Then along with this, inside the node itself, I should also have a weight stored here. 1 to 3 is 4 and 1 to 4 is 6. Likewise, you can fill up all these. So along with the vertex number, the weight of an edge is also stored inside the list itself. So now it will be called as cost adjacency list. So that's all about these two representations. Now next, let us look at compact list representation. In compact list representation, we will have a single dimension array for representing a graph. What should be the size of that single dimension array? See, the vertices are 5. We should have number of vertices, plus as each edge is represented in two ways, that is 1 to 2 and 2 to 1. So 2 times of edges, and I should also have an extra space. So how much it is? 5 plus 2 into 7 plus 1. This will be 20. Then one more thing. I am starting indices from 1 onwards. I am not using index 0. So for that I need one more extra space, that is 20 plus 1, 21. So here I will draw an array of size 21. So here I have an array of size 21, indices starting from 0 up to 20. So total 21 spaces. Then how to represent this? See, this first 5 locations are representing vertices. There are total 5 vertices. So first 5 spaces. I am not using this index 0. So from 1 to 5 they are representing vertices. Total 5 vertices are there. Then for each vertex I should have adjacency list, means who are adjacent to it. Like for vertex 1, adjacent vertices are 2, 3 and 4. But now I will not be using weights. I will remove these weights. So for 1, adjacent vertices are 2, 3 and 4. So this I have to write down. So where to write down this? See here, leaving this location vacant. I will not use that location. I will show you why I am leaving it vacant. So from here 2, 3 and 4. These are the adjacent vertices of vertex 1. See, the adjacent vertices of vertex 1 are 2, 3 and 4. They are starting from index 7 and ending at 9. So I will write down that 7 here, just 7 here. This means that the adjacent vertices of vertex 1 are starting from index 7, that are 2, 3, 4. Then where they are ending? They are ending at 9. So I did not mention that. I have just mentioned the starting point. Now let us take other vertices. For vertex 2, the adjacent vertices are 1 and 3. So I'll mark them 1 and 3. So these are from 10 to 11 only, just 2 places. So that is starting from 10. So that 10, index 10, I will write here. This means that the adjacent vertices of vertex 2 are starting from index 10 onwards. So 10 and 11, they are ending at 11. Now, as we have there 7 and 10, now observe this. The adjacent vertices of 1 are starting from 7 onwards. Okay, 7, 8, 9, stop. Why? Because the next location belongs to 2. So 7 and 10 together gives the starting and ending point for vertex 1. So that's how just we keep the starting index of adjacency list of vertices. Next, let us write down rest of those. That is for 3, the adjacent vertices are 1, 2, 4, 5. 1, 2, 4, 5. Starting index is 12 and this belongs to vertex 3. This belongs to 2. Then for 4, 1, 3, 5. So 1, 3, 5. These are for 4 and the starting point of this one is 16. Then for 5, adjacent vertices are 3 and 4. So these are 3 and 4 and the starting point is 19. This is starting point 19 and this belongs to 5. I have filled all of them. Now from 7 to 10 minus 1, list of vertices 1. From 10 to 12 minus 1, 11. List of vertices for vertex 2, these 2. Then for 4, 16 to 18, yes, 16 to 18. Then for 5, 19 to what? 19 to what? 19 to 20, means 21 minus 1. So here I should write down 21. So it gives the ending point for this vertex list of 5. That's why we have kept this place blank, so that we can store the index that is outside the size of an array, that is 21. 19 to 20 minus 1, 20. So that's it. This is the compact list representation. I have not stored weights. If you want to store weights, then you should have one more array. It means two-dimensional array, 2 rows and 21 columns. And each location you can have the vertex number. Below that you can also have its weight. Then what is the space consumed by this one? This is number of vertices and number of edges 2 times, so plus 2e. See, this we call it as n and this is 2e. If we say e is also equal to n, this is 2n. So total it is 3n. It is order of n. So it's linear. If we assume that n and e are equal, if we assume, they are not equal, but we assume. So why we are assuming is n is a linear value, e is also linear value. It's not e square, right? E square means quadratic. It is not n square. N square means quadratic. So this is also linear, this is also linear. So both are linear. So n means this is not variable n. This means linear. So the space consumed by compact list is linear. That's all. So in the coming videos we will see algorithms on graphs.